Okay, so today we're going to be talking about the friction lab. From our pre-lab discussion, we were able to kind of figure out that friction would be dependent on two things. We've got the type of surfaces involved and the normal force, not the force of gravity. Now, we were able to pick out normal force rather than force of gravity because when I held the eraser into the wall, it's stuck there. And when I decreased the force that I applied with my hand, so did this normal force. And when that decreased, friction, the static friction keeping the eraser where it was, went away, allowing the eraser to slide down. Notice the whole time the force of gravity remained the same. So of the normal force and the force of gravity, it's really the normal force that is the cause of friction. So in our lab setup, we were able to use our friction tubs to conduct this investigation, and each group had cork, felt, and nylon, some type of plastic, and our system was a tub. Now, if we were to do a force diagram, we were instructed to pull the tub at a constant velocity. So our forces here is a force of gravity on tub by Earth, and the normal force on tub by surface. And in this case, the surface that we're using was a plank of wood. And we knew that these were equal because it was neither accelerating, it was not accelerating up or down. Now, we pulled to the right. Some people had strings, other people did not. But either way, there is this force from the force sensor, and that's what we got from Logger Pro. And there's also this force of kinetic friction. And these are equal to each other, as long as we're pulling at a constant velocity, right? In the pre-lab, I told you that we would be looking at two types of graphs. The first type would be the frictional force versus time. And here are the different parts. Here we see that it starts off flat. This is the reading that the force sensor would give you. So here, at the flat part, we would have no force applied yet to the tub. And then we would increase the force applied to the tub until it reaches a max point. Now here, it's not moving yet. So this is actually called, this is where static friction takes place. This part here. And it's after this part where we begin moving. Which means that during the flat part here, we have the data point that we want if we were to take an average. So here, we've got kinetic friction, and this is the point that we wanted to take. So I instructed you to highlight this part. There would be a lot of jaggies there. So we use the stats button to get an average here. And we were plotting, we were using the average for our data point. So in the post lab, what we did was we compared our graphs. They all yielded linear plots. And we found that the roughest surface to wood interface would be the line with the greater slope. So we found that cork had the greater friction, and then felt, and plastic. Now here, we've got the slope is called the coefficient of kinetic friction, okay? With this being called the coefficient of friction being the Greek letter lowercase mu subscript k. And here are our two equations. We notice that they're both of similar shape. We've got the kinetic friction for moving objects, and we've got the static friction for non-moving objects. Notice the static friction equation is an inequality. Now, the reason why is because it actually takes the form of many values. So here we've got a maximum, and remember, this is where that peak happens. This is the maximum amount of static friction. Anywhere beyond that, motion starts to happen, and the object will start moving. But that's not to say static friction only has to be this value. It's every value before that too, up until 0. Okay, so those are friction equations, and we'll talk more later.